Hey everyone, and welcome grade 8 physical science students to today's explainer. I am absolutely thrilled to have you here today because we are looking at one of the most fundamental everyday processes in the universe, how thermal energy actually moves from one place to another. Have you ever wondered why some things feel instantly cold to the touch while others feel warm even if they're sitting in the exact same room? Or think about this. How does the heat from the sun actually manage to reach Earth across millions of miles of completely empty space? Well, today we are going to unlock the secrets of heat transfer. We're going to explore the incredible mechanisms that govern how energy shifts, how it moves around, and how it impacts our daily lives. Okay, let's dive into this. Here is our agenda for today. 1. The heat transfer mystery. 2. Conduction, direct contact. 3. Convection, fluids moving. 4. Radiation, no medium needed. 5. Tracing the fireplace. And finally, 6. Recap and transfer.
Section 1, the heat transfer mystery. Why does tile feel colder than carpet?
So I want you to imagine waking up on a chilly winter morning. You swing your legs out of bed, and your bare feet hit the soft, fluffy carpet. It feels pretty comfortable, right? But then you walk into the bathroom and step onto the tile floor. Instantly, you get a shock. The tile feels freezing cold against your bare skin. But why does that happen? Well, here is the incredible twist to our mystery. The carpet and the tile floor are actually at the exact same temperature. Seriously, because they've been in the same house all night, they're both just sitting there at room temperature. So why does one feel drastically colder than the other? The answer lies in the rate of heat transfer. You see, the tile material removes heat from your skin at a much faster rate than the carpeting does. It's not that the tile is physically colder, it's just stealing your body heat faster. This sensation of cold is actually just the feeling of thermal energy rapidly leaving your body. To understand exactly how the floor is pulling this off, we need to look at our first mechanism of heat transfer. Section 2. Conduction, direct contact, particles colliding to transfer energy. The absolutely crucial point here is that conduction happens when two objects are physically touching, right? Direct contact. At the microscopic level, particles in a hotter object have higher average kinetic energy, meaning they are vibrating and moving around a whole lot. When they come into contact with a cooler object, these highly energetic particles physically collide with the slower-moving particles of the cooler object. It's these literal collisions that transfer the energy, moving it from the high-temperature region directly to the low-temperature region. Now, some materials are just way better at this than others. Metals, for instance, are fantastic conductors of heat. If you've ever touched a metal desk or a laminate counter, you felt it pull heat right away from you. Materials like wood, plastic, rubber, and yes, your bedroom carpet are poor heat conductors. We call those insulators. So, going back to our mystery, the bathroom tile acts much more like a conductor, rapidly colliding with the particles in your skin and transferring your thermal energy straight into the floor. Section 3. Convection, fluids moving, heat transfer driven by buoyancy. Now, before we look at how this specific mechanism works, just a quick reminder that in physics, a fluid means either a liquid or a gas, okay? Both the water you drink and the air you breathe are fluids, and they move very differently than solid materials do. Convection is heat transfer driven entirely by the movement of these fluids. Imagine a pot of water boiling on a stove. As the water at the bottom of the pot heats up, through conduction from the burner, by the way, it expands. And because it expands, its density decreases. This hotter, less dense water experiences buoyancy, which is basically a tendency to rise to the top. When it rises, the colder, denser water at the top sinks down to the bottom to take its place. This creates a continuous rolling convective loop. And guess what? The exact same thing happens with the air in your house. Hot air from a heater rises, cools off near the ceiling, and sinks right back down. This is exactly why we use weather stripping on doors to control air movement and keep our homes nice and warm. All right, it is time for our first pause check. Think carefully about what we just learned. If you accidentally touch a hot stove burner with your hand, is that heat transfer by conduction or convection? Go ahead and pause the explainer for a second to lock in your answer. Got it? Okay, the correct answer is conduction. Touching the burner involves direct physical contact between your skin and the solid metal of the stove. Those particle collisions are transferring the heat directly. Now, if we were talking about the moving water boiling inside a pot that's sitting on that burner, well, that moving fluid would be convection. Make sense? Section 4. Radiation. No medium needed. Heat transfer via electromagnetic waves. This one is fascinating. Unlike conduction and convection, radiation requires absolutely no physical matter, no solid, no liquid, no gas to work. None. It transfers heat entirely through electromagnetic waves. This includes infrared radiation, visible light, microwaves, and even X-rays. Because it doesn't need a physical medium at all, this is exactly how the sun warms the Earth. The space between the Earth and the sun is a vast, empty vacuum, so convection and conduction are literally impossible. Instead, the sun emits electromagnetic radiation that travels all the way across empty space and is absorbed by our planet. Interestingly enough, the rate at which an object absorbs or emits this radiation depends a lot on its color. The color black is the absolute most effective absorber and radiator of electromagnetic energy, while the color white is the least effective, acting almost like a mirror that just reflects the radiation away. Let's do pause check number 2. Why is a black asphalt parking lot hotter than the green grass right next to it on a summer day, but then somehow becomes colder than that exact same grass on a clear summer night? Pause the explainer right here and think about how radiation works with color. Ready? Okay, here is the reasoning. During the day, the black asphalt absorbs electromagnetic radiation from the sun much better than the green grass, which causes its temperature to absolutely spike. However, the reverse is also true. Black objects radiate energy away much faster than green objects. So when the sun goes down, that black asphalt emits all its stored heat out into the night sky rapidly, making it colder than the grass by morning. Pretty cool, right? Now, what's really interesting about this slide is Section 5, Tracing the Fireplace, Real-World System Analysis.
In the real world, these 3 mechanisms don't just happen one at a time in isolation. Very often, conduction, convection, and radiation are happening simultaneously in the exact same system. Imagine you're sitting near a crackling fire in a living room. Step 1. As you sit in front of the fire, your skin feels warm even though you aren't touching the flames. That is mostly infrared radiation traveling directly through the air to your body. Step 2. The air inside the fireplace gets heated, becomes less dense, and rises straight up and out the chimney. This actually draws cold air into the room from around the windows to replace it, creating a giant convection current. Step 3. Meanwhile, the burning logs are in direct physical contact with the brick base of the fireplace. Heat is slowly transferred into the bricks and the surrounding floorboards through those particle collisions we talked about, which is convection. One single fire, 3 incredible methods of transferring thermal energy all at once.
Section 6, Recap and Transfer, Putting it all together. And this brilliantly illustrates our big 3 mechanisms side by side. Let's summarize. Conduction requires a physical medium, specifically direct contact, usually between solids, like your bare feet on that cold tile floor. Convection also requires a medium, but it must be a fluid, meaning a liquid or a gas, where warmer parts rise and cooler parts sink, just like water in a boiling pot. Finally, radiation requires no medium whatsoever. It can travel right through the vacuum of space, just like the sun's heat reaching Earth. Keeping this mental toolkit handy will help you analyze almost any heat transfer scenario in the world around you. Before we sign off today, I want to leave you with one final transfer question that ties today's lesson into a concept called specific heat. Now, specific heat is simply a material's resistance to changing temperature. So imagine a farmer is monitoring both the soil temperature of a field and a nearby pond as a freezing winter sets in. Based on our source material, soil has an approximate specific heat of 800 joules per kilogram degree Celsius, while water has a massive specific heat of 4,186. Because the soil has a significantly lower specific heat than the water, which one will reach 0 degrees Celsius first? And why? I enthusiastically challenge you to take what you know about energy transfer and specific heat to figure this out. As a hint, water can absorb and release a tremendous amount of energy with very little temperature change, which is exactly why oceans moderate our global climate. So think about what that means for our farmer's little pond. Keep asking questions, keep observing the world around you, and I will catch you in the next explainer.